rows. Follow root. Okay, then what?
Maybe go to the left of root if it is smaller, and to the right if it is larger, something like that.
Right. And the first one is root is null, is not null, right? That would be kind of an important one. Maybe we got to check and see if root is null. Maybe we don't. I don't know. We got to make sure we work with an empty tree. But certainly once you get there, you say, oh, this thing is certainly not null. So I need to check and see if I need to go to the left or to the right. And since 1 is smaller than 8, I know I need to go to the left. Right? Left is also not null, right? So there's a real number here. And so now that I know there's a number here, I have to look at it and say 1 is smaller, so I have to go to the left, okay? But notice left is null. So since it is null, then I know that I can go ahead and add the 1 at that appropriate spot, right? Now pay attention, there's something interesting going on here, right? Something interesting. Notice that the way that I knew that it would go right here is that I ran out of road. That's the way I would characterize it. I went off the road into null land. Does everybody see that? The only way I knew that this is where it went is I followed the left node of 3, and then I saw that that was null. Everybody see that? That's an interesting thing because notice it already seems like we went too far. We actually went to the left. It's not that we looked at 3 and checked to see whether left was null. We actually followed it and we actually went off the road and saw, yeah, I ran out of road, I went off, and now I know this is where it went. You see how that could be a problem? Right? Feels like a go too far kind of problem, so we have to solve that. Even though we didn't know till we hit this thing that it needed to go here, eventually 3 has to have its left child point at that, right? So that's the problem we're going to solve with x equals change x. 3 has to know that when we continue and go down to its left child, when we come back from this recursion, we might have added a new child there, right? That's the x equals change x. Every time you follow in this add method, every time you follow down, it is possible that a new child has appeared when you've moved, right? So you always take that into consideration. When you come back from that journey, you always have to reset that reference because it might be a new child this time. Okay, it was null before, now it's not. Now it's a node. Everybody see that? Okay, so we'll have to encode that. Okay, let's do one more. How about 12? Start at root, root's not null, bigger than 8, follow to the right, right's not null, bigger than 11, got to go to the right, right's not null, 17, that's bigger than 12, go to the left, left is null, we've run out of road, so we know that 12 has to go here as the left child of 17. Does that make sense?
Just to clarify, so instead of checking whether left and right are null, you just check whether the node that you're looking at is null. Like
that's right.
The parameter.
That's right. You don't even look at whether this node's children are left or null. You actually just say, hey, if I need to go to the left, go to the left. And it's not till you've actually gone there that you realize that's where it needed to go, right? You've literally gone, not just seeing that the end of the road is coming, you've actually gone off the road. And that's how you know it must go here. There are no more nodes. We hit a null. So it must go here. However we arrived here, it goes here.
Okay.
And the thing above me, whatever that was, has to fix up that reference. When I get back from that journey, right, it has to fix up that reference because I need to add a new node here, right? Does that make sense? So the code isn't actually look at 3 and then before I take a step, I check and see whether 3's left side is null. That turns out to be unnecessary amounts of code if you understand x equals change x. You literally just go to the left. And then the next recursive round, you say, hey, null happened. I'm on a null node, null place. So therefore the node goes here. So I'll create the new node, right? And I'll return it. And we'll see that in the code in a second. Okay. Does that make sense, Alex?
Yeah.
Okay. So here's the general algorithm. If we've run out a road, the node goes here. That's the only way we know that we actually have a spot for the node, is that we ran off the road, right? We ran into the ditch and we go, oh, I guess we're here because there's no more nodes. So this is where it must go, right? We ran to the end of the road, so now we got to build here. Then we look and see if it goes left or the right. And then we got to figure out, does it work on an empty tree? That's a whole other matter that we have to figure out. Okay, so now let's go write some code for it and see how it works. Okay, so the first thing to note with these recursive methods, you very often have a public facing, a client facing public method, and then you have a private method. The reason is the private method is going to be recursive and the public method is not. So we typically will have something like this, which is, like new node data, or data, whatever you want to call it, new node data, right? So we very often are going to have a public one, and then we're going to have a private one that looks very similar to it, except what? It's going to be private, and it's going to have one more parameter. And that's going to be where this particular journey needs to start. And that's going to be a binary int tree node called start node. Because what this is going to say is for each recursive call, we need to pick up wherever we left off, right? When you do a recursive call, you have to know where you're expected to start, and you're going to pick up at that point and then continue the search. So with this kind of thing, you're almost always going to have these two methods, a public front end that has fewer parameters, right? And a private one that has this one more parameter, right? And now we got to figure out how to write the code that does the right thing here. Okay, and we're going to go back and fix this up. We're not done, right? This is not all finished. So now let's start to think recursively and see if we can follow what we talked about algorithmically on the last slide and put it into play here. Okay. Oh, something bad is happening. Can you still hear me? Oh, okay. I got the circle. I was worried I got a little circle of death thing. Okay. You still hearing me?
Mm-hmm.
Good. All right.
Shouldn't that second add be in the node class because it references nodes and those are private?
Nope. It can reference nodes all it likes from right here.
Okay.
Yep. It's perfectly good. This is a list method, right? This is not a node method. This is a list method.
Oh,
Okay?
I just missed that it was private. That's my
Yeah, it's private. Yeah. Okay. So follow the logic. What is my base case? Remember, all recursive methods should have a base case and a recursive case. What's my base case based on what we just talked about on the previous thing?
Not null, maybe.
How do I say if I ran out of road?
If start node equals, yeah.
If the node I'm on, which seems weird, right? If the node I'm on is null, that's my base case, right? Otherwise, now I have some other cases. But what is it that I need to do here, right? If I found that I've run out of room, I know it goes here, so I need to make a new node, right? So binary int tree node, a new node equals new binary tree node, and I'm going to pass along the new node data, right? I need to make a new node, and then the node goes here, right? The node goes here. How do I say the node goes here?
Start node equals new node.
Right, exactly that. Right, start node equals new node. I need to point start node to a different place because it was null, now it's not, right? I've filled it in with something. So I need to make a new node, and then I need to point start node to that thing that I just made. But via x change x, we know that us changing start node is not going to solve the problem, right? That's not going to change the caller's reference. So however I got here, I've got a parent that needs to know about me. So since I want to literally change and make start node point to something, what do I need to return here?
Binary search tree node.
I need to return a reference to a node, a reference to a node. And then up here, this thing is going to have to use that, right? This thing is going to have to use that. In fact, the public call here is going to be the recursive call that says, hey, add the new node data, right? But start at the root for your search, right? You got to start at the root for your search. And in fact, right? And in fact, guess what might have happened during this thing? What might have happened to root itself? Because what if it's an empty tree? You run out of road right away and you put the node here. So what's happened to root?
Root is now the new node.
We have to repoint root here as well. X equals change X. Here's the X. Here's the thing that changes it. Here's the X, right? Root itself might have been referenced differently now, right? The first time you add a node, root is going to change. So via X change X, even this very first call, we have to do that, right? We have to say, hey, root might be different. We don't know. So let's repoint root just to make sure. This thing returns a node reference. You better take that node reference and do something with it. Go ahead, Ben.
But if we were already starting out, actually, I don't know if this would be an actual situation, but if we have it, if we're already starting out with the tree, and then we add, and then we're reassigning root to
Yep.
the add, then that would be a different sort of.
In this case, if the tree already exists, root hasn't been updated, but we still reassign it, right? So we're still doing a copy of that array, or sorry, that memory location, right? So we're doing an unnecessary copy, but we take that hit because it's not that big of overhead, right?
Got it.
Every time except the first one, that's actually a wasted copy, but we don't know, right? So we just reassign it anyway.
That makes sense. Okay.
Right. And having an if statement to see if it's different is actually just as expensive as just assigning it anyway, right? So an if statement would be less efficient, right? Okay. But this stuff looks weird when you see it, right? It looks weird. Let's see if we can get the rest working and then see if we like it first, and then we'll go figure out how to move forward. But let's do one more. What's the else case? I didn't run out of road. That means this node is a valid node, right? I didn't run off into the ditch. I'm on a non-null node. So now how do I have to proceed?
You have to figure if it's less than or greater than.
Okay, so if the data that I have in hand is less than what?
The start node data?
If this data that I'm looking to find the place for is less than start node's data, then what do I need to do? How do I say, go on with your search to the left?
Start node first here.
Start node to the left. You might check.
I have to recursively call, right? I have to recursively call add. I have to pass along the new node data. But now where is that recursive call going to start its search?
Start node dot left.
Yep. Continue the search, but take my left child as your starting point. And then, of course, that left child might have been repointed in this process. So what do I have to put at the front here? X equals change X. What goes here? Right? I might have a new left child, right? When I come back from whatever this is, a new child might be here. And so I need to make sure I point to it. X equals change X, just like X equals change X. Here's the X, here's the X, here's the X, here's the X, right? Now, why is this complaining? What did I finish? Start. Oh, I forgot to call add. Yeah, I forgot to call add. That would be better. Yeah. Okay. Does that make sense? And then what's my else?
So then we have to return start node. Right, yeah.
That's it. We've just written our first recursive craziness. Okay. If you don't understand X change X, this is tough, right? This is tough. But I promise you, it's a lot smaller than the code that you would write if you're not using X change X, and I'll show you a sample of the difference. This assumes, hey, if I go left, if I send you on an excursion down my left child, I might have a new child when we come back. So I've got to point to it, right? Left, maybe I was pointing to null now, and maybe I'm not pointing to null when I come back. So I have to repoint. Now, again, 99 times out of 100, the tree's already here, and I'm reassigning unnecessarily, right? But I always repoint just in case. Okay, in case my left child is now a different child. Maybe there's some remove code that's going to take it away. Maybe whatever it is in the add process, I'm creating nodes as I go. So I might have a new child. I better do the thing, right? This is interesting. Look at the little icon over here, right? The little recursive icon, right? It's a recursive call. That's fun. Okay. Any questions here? Right, so that's the prototype. Now let's see if it works. So here I'm going to say binary search tree int, my tree or my ints equals new binary search tree. And if it works, I should be able to say my ints.add, and I should be able to add some numbers, right? Why is that complaining?
It's not in main function.
Oh, sorry. Yeah, I always do this. Get excited. Public static void main. There we go. That's better. Thank you. Anybody else ever done that? You stare at that code like, why won't it compile? It looks perfectly valid. Well, it's because you're not writing in the right space. 3, 17. Let's do a smaller number, 4, and then let's do something in the middle there, 9. Sure. Okay, so let's put a breakpoint right here. I'm just going to write some stupid code so I can put a breakpoint, and then I'm going to debug it and going to see if this will do what we expect. Since we don't have any tree traversal code, we got to do this. So let's see what we get. All right, so let's see what our tree looks like. I'm going to bring this up and let's look at it. So here's my tree. Here's the root. Okay, data in the root is 5. It had to be, right? Because that's the first thing we brought in. And then let's see, to the left, here we have our 1 to the left. And then to the right of that, we have 3. To the right of that, we have 4. From the root's right, we have 11. To the left of 11, there's 9. To the right of 11, there's 17. That's our whole tree. All right. So looks like the tree was built properly from what we can see there. All right, any questions about what we've done so far? Let's stop and chat, because this code is very hard for your brain to understand when you've never written one of these before. This seems like weird stuff, right?